Yeah. So there, awesome, awesome. So I wanted to do a couple quick things before we got into analysis. First, I wanted to make sure I explained why you guys went through like the first 5 or 6 button pushes on that in-class quiz. So first of all, if you'd be so kind, fire up your TIs. We're not going to erase your data, although we're kind of done with it. This is a beautiful analysis. We'll come back to that momentarily. What I'd like everybody to do, everybody in here, press the math button. Darker. Press the left button and either press enter or 1, and you'll see the RAND command. RAND. Then just press enter. Now I got 0.93 and some change. And I'm guessing you guys didn't. You got something different. And that's kind of indicative of the fact that we all got a different, what kind of number? What's RAND stand for? Random. Random. So what the RAND command does is it randomly generates numbers between 0 and 1. So about 93% of the way, you guys got any number of differences. But the problem is that a computer cannot be random. It can't. I dealt with this on at the Coast in my second presentation when somebody told me how Excel, one of the more refined ways Excel is not purely random. So everybody do this. Everybody type, I'm going to give you a number. 7. Everybody type 7. Now press the STO button that's right above on. Now press math left 1 or enter. So it should look like this. 7 store RAND. Okay? Press enter now. So essentially what we just did was we did the same thing you guys did in the first part of your quiz, but we all seeded to the same thing. We all seeded to 7. Okay, ready? Press second enter.
Could you please repeat again?
And then 7? Press, just hang tight, you'll see the point here in a second. And then press second enter again, and you'll see the RAND word come up right there. Now press enter again. Every one of us should have that exact same 10 digits on our screen now. This is the problem with a computer. A computer cannot be random. When you get those things from the factory, they've all been seeded to 0. So essentially 0 stored into RAND, you'll all get. So if we did this quiz without seeding a different value into the randomizer, we'd have a bunch of box plots that were all identical, which is kind of pretty, but not good statistics. Because if I saw that, I think something was up. So that's why I made you all use your birthdays, because I figured birthdays, if we include the year, is a pretty good, even though we had some close birthday matches as far as that goes, like April 14th and April 15th, as soon as you put the year in there, you become very, very different numbers. So hopefully we got enough difference in the, and it looks like we did in the data sets, because look at our box plots. They're all slightly different, which is exactly what I wanted. So that explains why you guys had to go through that shebang. And now we should be good the rest of the term. Every once in a while I have you reseed, because sometimes if you do a memory dump, it'll reset it back to factory settings, which ends up unrandomizing it again. But that just explains that for you. So just keep that in the back of your mind. It's not important to memorize or regurgitate. Just that's why I had you do it. I want to focus on this. I want to focus on this right now. So the only thing that you have to have on your quiz to get 10 points is 5 numbers. The 5-number summary, which all of you pretty much put on your box plots up here, which is fantastic. So your minimum value, your lower quartile, your median, your upper quartile, and your max. So what do you think? What do you think? These are all different. They're all slightly different. What makes perfect sense? We're all sampling from a 93 or 94 year range of snowfall. But are they vastly different from each other? What do you think? What do you think? Aren't they, though? Yeah. Aren't they kind of grouped together? I mean, if you can think of it, there's part of the box is shared in every one of those box plots. You can kind of get it right down the middle, right here. Mm-hmm. That's in every single box plot. Granted, the boxes are slightly wider and slightly narrower in some places. But there's definitely, sure, and the distribution in general, did you guys notice, how many of you got slightly skewed histograms when you did your histogram graphs, you got slightly skewed histograms? Yeah, we've got some skew in here. There's some higher values that are more away from, if you will, center than the lower values, for sure. And your average is probably a little bit higher than your medians, if you raise your hand for that a little bit. And that's a consequence of skewed data. But be that as it may, other than this guy right here, the rest of them seem to be hovering down here, and the boxes are down here. I guess purple and black are kind of like over that way a little bit more. But you don't see any boxes way over here. There's no boxes up here. Because if you're randomly selecting from that data point, I mean, if you look at those of you playing the home game, this is the data set we're using. Hello. There's an awful lot of data points down here and not as many up here. So if you're randomly selecting from the data points, you should be getting more, if you will, down this way than up that way. So even though we're getting different box plot representations, we're still getting essentially the same thing on average. And I'm saying this, I'm saying these are the same statistically, which would drive a mathematician nuts because they think, oh, there are 10 unique box plots, and there are. But statistically, I'm seeing exactly the same thing. Jada, go ahead.
So what the things look like, that has nothing to do with our birthdays, right?
No, the birthdays were just what years you got.
Okay.
So it would tell you all that was governing was which years, when you went back to L1 and sorted it, it's what years you got in there. And how many of you guys got repeats in the year list? Good. Yeah. There's enough of a sample from a small enough population that you should be getting some repeats in there. And yeah, a bunch of them. That's pretty cool. We'll deal with more of that probability idea, that percentage of occurrence as we get through the course as well. So this is the point. This is a great way of comparing data sets. Box plots present a great way of, even though technically speaking, all 10 of these are comparing the same data set. Nonetheless, this is a great way of doing that comparison. Who's lived in Bend a long time? No, nobody's been here a long time. Okay. There's always been this is a very small class. Do you remember the winters when we get hammered with snow? On average, what do you think on those heavy years, on average, those heavy years, how much snow is on the ground per day, do you think? How much snow is on the ground per day? If you had to put a number to it, on those heavy years of snowfall. What do you think? 3 inches. Love it. Who would say more than 3 inches? Who remembers those days when you have to dig out, Armando's going to say.
I was going to say probably about maybe 5 inches.
5 inches, good on those heavy years, good. After seeing this, and some of these years are ridiculous, even 2012, I mean, by my data, and again, my data was collected on the northeast side of town, which tends to get less snow than over here, just because it's lower elevation. I think it's 400 or so feet lower than COCC is, so it could be snowing here. That day when we got nuked on, it was raining at my house, and it rained very little, and the sun came back out again, because we're on the tail end of the butte, kind of the rain shadow, if you will. So I was interested in this, so I decided to check out the same site. It gave me a really neat graphic. I'll share it with you guys too, just for trivia. Oh, I've lost it. Wait a minute, I must have closed it. 243 lessons, rel pause. There you are. This, oh, there it is. Here is the average daily snow depth from January 1st to December 31st, according to the same exact site, Western Regional Climate Center. Let's see if you guys can see this at home. Kind of. And what you notice is it's highest in February, right about Groundhog's Day, at 2 inches per. Now remember when I asked, that might fly in the face of the question I asked. I said, well, how would you guys average it? But I said average the highest snowfall years. This is on average, on record, all 100 of those years. So they're also averaging in the years where there was no snow on the ground. So basically, if you have 100 years, and you had 3.5 feet on the ground in February in 32, but you had 0 for the other 99 years, you have to take that 3.5 feet and average it over 100 years, which knocks it down pretty quickly. But our memories don't remember that. They tend to remember those big days when we lost school because we had to dig out our parents' car for 5.5 straight days. But that's indicated here, I think. It's just indicated in terms of an average. So I think that's really cool. I like the fact that there's all these little hiccups right here in May. I love that. Little hiccups in, well, I guess April going into May. And then starting just about November 1st, it starts back up again. Although we know we've had snow in October. It's just that it's so infrequent and so intermittent and so little that it basically averages to 0 over time. Does that make sense? So I thought that was kind of a clever way to analyze that.
What year is that?
This is all years. It's the same data set that this is on average snow depth per day over 100 years. So from I'm saying 100. It's 27 to 2000. I think this was the 2008. 2005. There it is. 28 to 2005. Yeah, they stopped making the 2005. I believe is when the guy stopped collecting data. Whoever was doing the Bend station. That's when Sean had to pick up the slack. So I have a little ruler up by the beehive, and I just run out there, and when it snows, and I write it down and collate it all by March 21st, and then we have another data point. It's a lot of freaking work. Because like, I have to remind myself to do it. Like from what is it, December 21st through March 21st, every day on Outlook it reminds me, go check snow, go check snow. Okay, okay. But I want you guys having the best possible day. That's all I'm saying. Speaking of best possible day, does this make sense? I want to do some more. I want to do some other data today. I do want to tie in, though. I'm going to turn this off. I want to look back at your plots. Did anybody, in addition to doing your box plots this way, do them modified? I think I made a mention at the very bottom. Nobody got outliers, did they? Nobody got outliers, did they? Right? Now, the reason I can tell is because there's a really cool graphical way of analyzing. Once I see your box plots up here on the board, there are a number of ways of tracking outliers. And we're going to look at all of those. Well, we'll look at a few of them today. We'll start today. We'll probably look at the rest of them on Wednesday. But one quick way of tracking outliers is using box plots. And this is how your TI tracks them. So for example, this purple one up, this is Jordan, this is you guys right here. In order to see if any of the data points are termed outliers, and I want to come back to that momentarily. I want to talk about what an outlier is. One way of saying it is, let's see if there are any that are too big or too small. It's a little bit of a limited definition. We'll come back to that. But what the TI will do is, mathematically, it measures this distance right here. Okay? That's called the IQR. We'll come back to why that's called that momentarily. It increases that by 50%. And then it stacks that on Q3 and below Q1. And if any of the data points are outside of my external finger, they're considered too big or too small to be usual, hence outliers. That's how I could tell kind of quickly that we didn't have any outliers in here. I just looked at the boxes and I doubled them, or I added 50% to each one. So here's a box, add 50%, stack, stack. All the data points are inside that, so there's no outliers there. There's box, increase by 50%, stack, stack, everybody's inside. That's one way of measuring them, and I want to come back to that with a little more formal analysis. But I can tell by looking at this that even this long whisker here, even though it's a long whisker, when I do that IQR box plus 50% and stack it, that small data point is still within that range, if you will, of acceptable non-outlier data points. So that's what I want to kind of talk about next, is we keep using this term outliers. So you guys happy with your quizzes? Mm-hmm. Let's hand them up here. Let's hand them up, get some, let's make a little pile up here. And now I want to tag this conversation of outliers into this, because it's a perfectly logical place to discuss it, I think. So we're going to start. We're going to start by collecting some data. I don't see any chairs without wheels on them. No, I don't want to use that one. All these chairs have wheels, don't they? All right. We have to use a desk. Oh, well then I'm going to stay on the floor.
Well, the back of the
I was going to stand up on the table. That's not a good idea. It's a recipe for me getting myself hurt. Busted my face. Oh, I got extras. Thank you, David. Perfect. We'll put yours right here. Muy perfecto. All right. So here's our next data set. Guess my weight to the nearest 5 pounds. Guess my weight. No, don't share it. Write it down, because I want each of you to have a guess. And then we'll collate it, of course. I want to look at it as well. Guess my weight to the nearest 5 pounds. With hair. We're going to guess that next. Oh, we could just, what is it, divided by 2.2 or whatever it is.
Doesn't matter. I got used to it.
That's okay.
Kilograms,
Is it 2.2 pounds per kilogram? Is that what it is?
I don't remember.
I think that's right.
But anyway, I'll try to do my best.
That's okay. We got Google. We can always use Google. 2.2. So you can always do kilograms multiplied by 2.2 and figure out what the pounds are. I think I said divide earlier. That was wrong. Yeah? Remember, the nearest 5. So, 100, 105, 110, 115, and so forth. I don't think anybody's guessing 100, but... Cool? Let's collect some data. I'm going to erase these beautiful box plots. What the hell? Leave them up there a little bit longer. We'll just go on the sideboard over here. So let's do guess Sean's weight. Let's hear some ideas. 175.
170.
170?
165.
165? Anybody go below 165? What do you got, Liz?
155.
155? Anybody below 155? Okay, we got a low end. So we're gonna do X equals weight guess. Well, we'll make a little frequency chart here. This will be our first data set. This will be our first data set. So I heard a 155. So that means we may have a 160, maybe. 165, I heard a 170, I heard a 175. Anybody above a 175?
Actually, I put down 185.
185, totally fine. 185, anybody above 185? Any 190s? Any 190s? Okay, so that's our range of data. Let's get some frequencies in now. So Liz, you're 155, right? I'm guessing that was the only one. Any 160s? Got one 160, two 160s. 165s. There. 170s. 7, okay. 175s. 1, 2, 3 of those. 180s. And a 185. Got the one? Cool. Awesome. All right, friends. Calculate as much as you can statistically for that data set how to summarize it. Everything you've learned today. Give me a summary. Give me a graph. Give me a couple graphs, actually. Give me summary statistics. Describe that data set using as many different summary statistics that you have at your disposal right now. This is kind of like, if you will, we're in week 5. We're at the halfway point of the course. So we're kind of in that section where we're making the transition between pure statistics to statistics and probability. So this is a good time to just remember how to do all this wonderful stuff. And I'll get the same data in my TI as well. Actually, I don't know why these box plots. They're beautiful. I hate to erase them. We don't need them. I'm going to turn two graphs on, so it's okay with you guys. I'm going to turn on a histogram and a box plot. Because one gives us a shape, which is great, and one gives us the relative position, which is also great in a different way. So I'm going to turn on plot 1 and plot 2. Plot 1 will make the histogram. Remember to change one thing you have to get kind of supple in your mind with is changing the X list and frequencies back and forth. Like right now it is L21. We very rarely do that unless you put your raw data directly into L2. Usually you're going to have L1 in one, or in this case, L1 and L2, because you have your data in L1 and your frequency in L2. And the L2 is pretty important. I noticed a couple little errors on the in-class exam I just gave back to you, and I could tell what happened. It was on the newborn baby weights. It was in kilograms or grams, whatever it was. I forget, it was kilograms. And I could tell when people forgot to put L2 in when they did their calculations. They put in, 0.25, 0.5, 0.751, and then just ran one bar stats without accounting for the frequencies that were there. So you'll get used to this since we're not going to stop doing it. But that's one of those things that kind of make a mental note of right now. Histogram, yay. Plot 2, we'll turn that on and make already set up, L1, L2. Okay, we'll go with a little zoom stat. Because I pressed the wrong button. Zoom stat. There she is. I'm going to play with the window a little bit with your guys' permission. This is the same window we should all be getting if we do a histogram in a box plot. Although I like to tinker. I'm going to tinker with the Y to get the box plot off. I'm also going to tinker with the X scale. So the X scale is set at 6, which is kind of silly because our X scales are set at 5. So I want to change it to 5. And let's just see if let's see if X scale 5 in graph makes it okay. Nah, still got too high of a bar touching the box plot. So I'm going to change my Y max to say 20 ought to do it. There, that's not bad. It's probably too much. Probably 15 would have been fine. So, make sure we can see what we're looking at. You see Elena's guess? You see Elena's guess? Right there, separated out there by himself. Do we see Liz's 155? We have the 160, the 165, and so forth and so on. Okay, so we've got this beautiful graphic. Do we have some measures of center, i.e. spread or relative position? What was the average guess, my friends? 170 on average? Beautiful. 170 pounds. Did I put X bar, is that what you meant, Trev? X bar? Yes. That was it. Good, matches your mode. Matches the mode. I'm assuming it matches the median as well. Looks like it does, right? Median comes up to be 170 as well. Definitely 170. What's the plus or minus on this bad boy? Let me see if I can approximate it. Hang on. I want to pretend that's bell-shaped data-ish. Okay? And I'm going to say, let's just say 155 to 1, this was 85, right? So it's 30. 7.5? What do you guys get for standard deviation? 7.3. 7.3? I'm not going to brag. It's pretty damn good. Now, what the hell did I just do? I said it was 7.5. Haley said it's 7.3. I'm feeling pretty pumped right now. How did I do that? Was that magic? Let's walk through what I just did. First thing I did, I went like this. You did something similar on your take-home exam that you handed in today. I went like this, and I went like this and this. What am I doing essentially right here? Approximately, what am I doing?
The outliers.
Is that good? What am I trapping in here, Elena? What percent-ish?
75.
What, more than 75? 95. I'm ish trapping where 95% of the data appears to be. Now, I know it's hard with a class this small. There's only 20 of you in this class. So I have to trap 19 of you, which is essentially what I did. I trapped, well, there aren't even 20 people here today. But I threw out the low and the high, and I trapped the middle. So then I said, okay, how far apart are those? Well, this is 155, and that's 185. So that's a distance of 30, isn't it?
Mm-hmm.
If I'm calling that 2 standard deviations, that means starting in the middle, adding 1 and adding 2, I've moved 4 standard deviations from bottom to top, haven't I? Think back to the weight loss data that we talked about in class, talking with variation. If I start at average, and then add and subtract 1 standard deviation, that's S up and S down. That's 2 S's distance. If I do it again, that's 2 standard deviations. That's 2 more S's. That's 4 S's. So essentially, if 4 S's spans 30 pounds, 1 S has to span 30/4 of a pound, or 7.5 pounds, or 7.3 pounds. Don't be all picky about it. So your standard deviation around this average is about 7.3 pounds. About 7.3 pounds. What I want to do right now is I want to chit-chat about one way. You mentioned, Elena, I threw out the outliers. I love when you said that, because that's what I kind of want to chit-chat today about. In addition to what we just got done talking about, which is these wonderful box plots and relative position, I want to talk about this outlierness, okay? So one way of measuring outliers, I'm going to turn this off just for a second. I want to use the board for notes. One way to measure outliers and let's swing the camera back to center here, because this is a little bit righty. Now, I want to preface this by saying, friends, this is created by people. This is not like in some Bible somewhere. This is what people have decided is a good measure of outliers. And I agree. I think it's a really good measure of outliers. So, there's a big if that goes with it, though. If your data is bell-ish shaped. Exactly. And you have to start with that if. I like the data you guys just gave me. I'm going to call it bell-shaped. I'm going to call it bell-shaped. Looking at Pearson's, Pearson's is essentially 0. Pearson's is that thing you didn't like very much in your homework, the PSSC, where you take the difference in the median and the average, and then divide it by standard deviation. You don't remember. It's okay, you don't remember it. It's skew. It's that skew measure. And essentially, since the median and the standard, since the median and the average are the same, the Pearson's is going to essentially be nothing, 0. And I look at the graph, and the graph looks like it's roughly a bell shape, so I'm happy there too. So if your data is bell-shaped, one way to measure outliers is you can make this statement. An outlier is any data point or data points